sometimes we'll have logs where we have to take the log of both sides to get the answer to the equation. And then we can actually use implicit differentiation, and that will give us our dy dx. So the easiest way to come about or find these problems is where we have very, very complicated looking examples. So in the case of number 1, you have x to the 3/4, the square root. You have all this craziness going on. So the idea is that rather than have to do a quotient rule with a product rule, I could ln both sides and then use my log features of being able to take division and turn it to subtraction, being able to take multiplication and turn it to addition. So what they're saying is if you have these really, really complicated looking functions, if you ln both sides, what we get is the natural log of y equals the natural log of all this, right? But what I want to do is I want to use my natural log rules and break it up. So I'm going to say it's the natural log of x to the 3/4 plus the natural log of x squared plus 1 to the 1/2 minus the natural log of 3x plus 2 to the 5th. And then the idea is the same. Bring out all your exponents as coefficients. So you get the natural log of y equals 3/4 the natural log of x plus 1/2 the natural log of x squared plus 1 minus 5 natural log of 3x plus 2. So again, everything in blue so far is still the original function. We've actually done no deriving or calculus. The derivative, and this is where it said you needed implicit, would this come from this? So the idea is, what's the derivative of the natural log of y? Well, instead of the natural log of x being 1 over x, now it's 1 over y dy dx. Three-fourths is your coefficient. Derivative of the natural log of x would be 1 over x dx dx. But I told you yesterday you're finally allowed to not write those. Plus 1/2. Remember, it's 1 over u times the derivative of u. So derivative of x squared is 2x. Derivative of 1 would be 0. Minus 1 over u times the derivative of u. We don't want a variable on the left. So if you have 1 over y, how would you move it to the other side? Yep. So you'd have dy dx equals y times all of this cleaned up. So you clean up the beginning, you get 3 over 4x. The 1/2 and the 2 would cancel. So you get x over x squared plus 1. 5 and 3 would give you 15. We don't typically like our answers to be in terms of x and y. So you have to back substitute one more time, recalling that y is really this whole original function. So had you done it like the Hody High minus Heidi Ho with all the quotient rules and everything, this is the GCF you would have ended up being able to pull up. So again, there is a connection, but again, those 5 lines are pretty gruesome. Could you imagine having done this using the Hody High and Heidi Ho?
Yeah, easy peasy.
Yeah. Okay, let's look at the next one. So we have x to the square root of x. We haven't seen this before. This is the case where you have a variable to a variable. That's different than the examples we did yesterday. Yesterday we did a number to a variable. So you have like 8 to the square root of x. We didn't have x to the square root of x. So a variable to a variable, if you would see it, needs to have you to ln both sides. So if you have a variable to a variable, you automatically need to ln both sides. Because we don't have a formula for differentiating this otherwise. You can't use the a to the u rule. It doesn't work, because that only works if the base is a coefficient or a constant that would give you that natural log of it. So we have to ln both sides. Bringing out that root x. And then deriving. So again, you have a product rule. So it's first times root of the second plus second times root of the first. So you have root x over x plus the natural log of 2 over root x. You could create a common denominator for yourself. So if you think about the fact here, this is 1/2 over 1. So if you simplified these, you'd get 1 over the square root of x. So all you're missing is the 2. Move over that y, so you get dy dx equals, and if you want, plug your y back in, it'd be x root x 2 plus ln x all over 2 square roots of x. So again, the next one is a natural log, kind of with a cosine of x up top. Since the cosine of x is outside the natural log, you can't use the bring down function rule, because this is not the same as that. Do you see the difference? You see how these parentheses are around the natural log, not around the x.
The whole thing.
So yes, we need to ln the whole function. So you get the ln of y equals the ln of x to the cosine of x. So that now I can bring that down. Now, so you have first times derivative of the second. So again, you have to recall that this is kind of like a chain rule, right? So the inside function is ln of x. So if you turn these to a u, the u is ln x. So u prime would be what? So if you derive this ln, it's 1 over u times u prime plus the second, which is all of this, times derivative of the first. Clean it up. Move over your y. So what I did was I turned the inside function to u. So I used the natural log of u rule, which is 1 over u times u prime.
Okay.
So, I mean, there's my u and my u prime, so there's my u and my u prime.
Okay. And where's the inner point?
Right there. The derivative of this is that. So the derivative of the inside is this.
I mean, so don't you have to do like, you're going to do the outer first. The whole outer would be 1 over ln of x times 1 over x. That'd be the whole outer. Then you have to do the inner right after, right?
She did that with the cosine.
Instead of trying to say outer inner, I changed it to the u in the u prime. So like by making it u and u prime, it accommodates for the inner.
Can you just write real quick, like in u prime, in terms of u prime, using u prime?
She did it with the cosine of x times. That's where she did the outer and then the inner with the cosine of x times 1 over ln of x.
I mean, just the ln part.
I did. I mean, ignore the cosine. I made it ln of u, where u is equal to the natural log of x.
Okay.
So the rule for ln of u is 1 over u times u prime. So here's my u, it's the natural log of x. The derivative of that is 1 over x.
Because don't you need another u prime? Because that's the inner part.
Right. We can do it on a calculator and I can like show you with the number plugged in. Okay? So that's, I mean the next one. So I guess the reason I put the next one on there is at first you look at this and you go, oh, it's an a to the u. You just have to be cautiously aware of the fact that this is different than the ones we've been doing. Not that you can't ln both sides, but you don't need to ln both sides. Because this one is our rule. This is a to the u. So your u is negative 1 over x. Your u prime, so it's like negative 1, x to the negative 1, would be a negative times a negative, which is positive. So now it's just your rule, which is a to the u times natural log of a times u prime.
Why would you calculate that on
Because that's the rule. Like the derivative rule for a to the u is that its derivative is the original times the natural log of a times u prime. So that's your formula. And if you wanted, you could actually drop that down too.
I'll do it on the whole.
Do you have one more example, or are you done?
Yeah.
You can see better.
Oh, it's more fun than oh, it is.
Do y equals 5. Negative 1 over x. I'm going to do it ln both sides.
ln y
So again, the question is, when you look at something like this, do I need to ln both sides or not? Does it fit any of our rules? Do I have a variable to a variable? What is x to the 1/2? Yeah, so it's really not as complicated as it looks. So I want you to just realize, don't fall into that trap of auto lning both sides. Because tomorrow it's not going to tell you when if you need to ln both sides. So you need to recognize that something like this is simply the product rule, yeah, where it's first times root of the second plus the second times root of the first. Okay, careful. First times root of the second would be 0. Yeah, because natural log of 5 is a constant. So it's second times root of the first, which is okay. So it works.
What we got? Yeah.
Alright. So it does work if you actually would have ln'd both sides. Because he ends up getting this answer right here also. So you see how he has like the y outside, which is this. That's wrong. So if you did it, or you forgot your ln rule for a's, it does work. That's all. I just wanted to see if it was gruesome or not. Yeah.
Well, I have a question, and you just erased the word.
Go ahead. I kind of know what it says though. What was your question?
It's like, I was confused on when you did partial why you canceled out.
Why I erased it?
Yeah.
Because the natural log of 5 is a constant. So he treated the natural log of 5 like a function. But the natural log of 5 is simply like a number. If you put it into your graphing calculator, it's like, I don't even know what the natural log of 5 would be. But it would be like 2.46, let's say. I know. I just said 2.46.
Wow, you're pretty good.
I have no idea. It would be small. Gosh, it's probably like 0.246.
She's so far off.
What's natural log of 6?
1.6.
Really? I said 2 and then 0.2. It was pretty much in the middle. I'd like to see your guesses be better.